Skewed data. How does one deal with skewed data? By the way, this is kind of off topic, but we're talking about it anyway, so there. Simplest answer is probably something called stratification. And the idea of stratification is you resample your data. Let's randomly pick a pattern. Well, I guess let me put it this way. What we want to do is have some data that has approximately equal class probabilities. So 50% zeros, 50% ones in the target label. So in our stratified data, let's pick a random row with a 0 class label. We could do that with rejection sampling. Just pick one, and if it doesn't have the class label we want, throw it out. We could do it by sorting all the data based on the class label, separating it into buckets. However you want to do it doesn't really matter. But suppose you pick some arbitrary pattern with a 0 and paste it over here in your stratified data. And then you could pick one that has a 1, and you'll paste that over here in your stratified data and repeat. And then you end up with a whole bunch of data with uniform balance between zeros and ones, right? There's always noise in data, so there will be a 10 too. There you go. Okay, and this garbage represents all the features. Now that you have stratified training data, you throw it at your machine learning algorithm, and voila, it often predicts that the Bitcoin market will crash, even though that's a very rare event. And now you get a whole bunch of false positives, yay, which is usually well, I hate false positives, but in this case we want them, and life is a little bit better, I guess you could say. So kind of yes and kind of no. You could imagine a case of continuous labels, because yeah, crash is a continuous concept, right? I mean, unless you threshold it, there's varying levels of crashiness. And I guess if you were to measure the distribution, it probably is a very long-tailed thing, like something like that-ish, where around here represents going up or going down just a little bit, and usually going up. And way over here in the long tail is this dramatic crashing. Now that's kind of weird that I put positive on the right side. Usually right is positive, and crash is usually a negative thing. So let me just redraw my distribution. If that's 0, I would bet the distribution of the delta, meaning the difference between today's price and yesterday's price, on the Bitcoin market will look something very much like, and by very much I mean scaled and stretched to fit whatever the heck it really is. And truthfully, we're not going to have enough data over on this long tail to really sample it well. So there's also going to be a difference between the true distribution that it follows and the histogram of actual samples that you can extract from the data. And you'd need a little bit of, I guess this is where you might want to talk to a statistician and figure out what's the distributions that it's likely to follow, and there's a whole bunch of analysis you can do to try to get it right. But so in theory, what happens a lot in markets is they're going to usually go up, but when they go down hard, and that rarely happens. And so that's why you've got this style of distribution. Now, so because of the way the data looks, if you just train a classifier to predict buy or sell, it often does a very bad job. It'll tell you buy, 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 and that'll make you money, and you'll be happy until you lose it all. Let's see, what were we saying? So stratification is one general purpose solution. Now, what you'd really like is a probability on these ones and zeros, not just a 1 or a 0. I kind of like neural nets for that. They give continuous values. They tend to be pretty good at fitting actual distributions. There's a lot of nice properties for neural nets. So yeah, when you have zeros and ones in the output, you just use a single output unit, predict a continuous value, and a whole bunch of analyses have been done on this, and they find that there's not really much need to calibrate neural networks to fit the actual distributions, whereas there is with lots of other models. They tend to kind of fit to the distributions themselves. Now, of course, that's only partly true, but in my opinion, it's a reasonable assumption that the neural net tends to conform to the true distribution given a crazy large amount of training data. So with neural networks, there happens to be an easier way to stratify data, because you have this thing called learning rate. And the idea of a learning rate is it impacts how strongly the neural network updates its weights. So if you're training a skewed data, if you're training a neural net on skewed data, what you can do that's, I think, is much easier is just when you happen to visit a positive class label, you can basically use a regular learning rate. And when you're visiting a negative class label, or an infrequent class label, you use a very, very, very tiny learning rate. And essentially your learning rate is the inverse of the frequency with which those classes occur, and then that works out to approximately the same thing as stratifying your data. One advantage of this is you don't have to take the time to pre-process the data. You're still going to end up visiting, it's going to be about the same as if you had visited the infrequent labels more frequently. And so it is going to overfit to those few occurrences that you have. So if you're trying to predict a market crash, what you're going to find is whatever happened when that market crashes, it's going to fit precisely to those conditions. And so you've got the problem of you're overfitting to the rare infrequent events, and that means it's possibly going to miss another similar infrequent event because it's overfit to the ones that are in your training data. And that'll happen whether you've stratified your data or just used a scaled learning rate based on the frequency of the labels. So how do you deal with that? Lots of good solutions. One of them is to regularize your neural net. And anytime you're trying to do statistically correct distributions, you've got to use a little bit of regularization. So the idea of regularization is kind of scale down your weights, add a little bit of pressure to the system to not overfit the data. And that will cause it to generalize a little bit more in the infrequent cases. So it'll build a little bit bigger of a bubble around those classes. And then when conditions like those occur again, it'll be more likely to recognize that, hey, this infrequent condition is about to occur. Another principle that I think is pretty useful is called jitter. The idea of jitter, so whenever you have skewed data, the big problem we're facing is not enough data for the infrequent event. And whenever you have not enough data, overfit is a major issue. So focus very heavily on not letting your model overfit. What jitter does is it creates samples that aren't exactly like the ones that are already in your data. So for example, if you're training on the MNIST data set of handwritten digits, you could jitter each digit by rotating it slightly, translating it slightly, boldifying or unboldifying the letter, maybe.
I guess the noise would just be randomly turning on and off some bit.
Yeah, so you can inject Gaussian noise. That's also jittering. If you consider the manifold of handwritten digits, pretend this represents a manifold, and this represents a digit. If you were to take a digit and rotate or scale or boldify it or italicize it or make various random perturbations, that's kind of like adding training samples over here and over there and over there that are on the manifold of digits, because those make reasonable handwritten digits, right? Someone could very well write a handwritten digit but stretch it vertically a little bit more than the one in your training data. So that makes a reasonable sample. If you inject Gaussian noise, that's also jitter, but it's kind of like rising vertically off of that manifold. You're adding training samples that are not reasonable. So when you jitter, one of the biggest problems you'll face is, how do you jitter intelligently? And alas, I don't really know the answer to that. So you'll have to deal with that. In the case of trying to predict Bitcoins, I think jittering the cases of when a market crash occurred, that's going to be rough. I think the best you could do is inject Gaussian noise. But hey, that's better than nothing. At least it'll create a bigger bubble around those cases of infrequent occurrences. Yes?
When we do random jitter, do we need to do it across all the data set regardless of level, or is it some specific level?
So what you need to do, I guess, is not well defined, because the whole purpose of jitter is just, hey, we don't have enough data, let's fabricate it. Let's pretend let's make some more data. And you can really screw yourself up by doing that, or you can really benefit yourself tremendously. It's a great way to fight overfit, but it only works if you jitter intelligently. So if you're going to inject Gaussian noise, you probably don't want to inject too much. Now, of course, if you inject too little, it's as if you didn't jitter at all. It's, imagine every point turns into a little cluster of points, but if each cluster is still vastly separated from your other training points, then what have you done? You want to jitter just the right amount that the data points kind of start bleeding together, I guess, and then you've got a better surface to fit. But even that's not the true thing the data did. The real thing you want is more samples. So all you really have to do is watch the Get Bitcoin market for the next 400 years. Then you'll have plenty of data, then you can train on it, and then you'll be able to predict it very well. Obviously, that's not acceptable. So in the end, it's going to come down to tricks and hacks. And that's unfortunately all it is. Jitter is just a trick to produce more data. It's a little bit better than merely stratifying, because rather than having a whole bunch of instances of the same pattern over and over, you have variations of it. And as long as you vary in an intelligent way, you'll be guiding your model to do something intelligent. Lots of other things you should be aware of is try to predict ratios rather than, let's see, here's another example. If you were trying to look at a market and the market looks like that, because that's kind of what markets look like, right? If your training examples were just the true values of the data, meaning this window is a training sample and for predicting what happens the next day, and this window is a training sample for predicting what happens the next day, and this is a training sample for what happens on this day, and then you present to it this training sample, and you say, what's going to happen the next day? The model will say, I've never seen anything like that before, because all of my training examples have been these values down in the low range, and this high thing has never happened before. So panic, what do I do? With a little bit of cleverness, if you just take today's value and then divide by yesterday's, the day before that, and the day before that, then you've got ratios going on. And now you can see that, in fact, this pattern here doesn't look all that different from that pattern here, because relative to the last day in the window, the ratios have gone through some pattern that kind of makes sense. And thus, you might be able to make more intelligent predictions in the future when you're actually trying to look at things it's never seen before. So this, I guess, is called invariance. And I don't know of the best way to achieve invariance. It really comes down to think about it a lot and do some intelligent pre-processing. But the more invariant features you can get into your prediction, the more you're doing an interpolation problem rather than an extrapolation problem, and that'll greatly enhance your ability to make predictions, so that the future crashes you're trying to predict are going to be much more like the past crashes that you've seen before, and thus you'll make better predictions, if that makes sense. Okay, that was a whirlwind of stuff, and I'm sure I gave more answer than I should have, but